Hello there, and welcome to The Weary Researcher. I'm so glad you're here tonight. Whether you're settling into bed, curled up somewhere quiet, or simply seeking a moment of cosmic calm, you've found just the right place. Tonight, we're going to drift gently through one of the most profound questions in all of science. What happens at the very end of time itself? Before we begin our journey to the ultimate fate of everything, I'd love to know where in the world you're listening from and what time it is right now in your corner of the universe. There's something beautifully fitting about pondering the end of time while we're scattered across different time zones, each of us arriving at this moment in our own unique slice of the cosmic clock. If you find this voyage through deep time soothing, intriguing, or just a peaceful way to unwind after contemplating existence, I'd be ever so grateful if you gave the video a like and perhaps subscribed. It helps this little corner of cosmic contemplation reach others who might need a gentle pause to consider the vast scales of space and time. Now, I do hope this isn't so fascinating that it keeps you awake, but if it does, well, at least you'll have learned something profound about thermodynamics and the ultimate destiny of the cosmos before you drift off to sleep. So settle in, slow your thoughts, and let's begin. Because somewhere between the tick of atomic clocks and the patient expansion of space itself lies the story of how everything ends. Imagine, if you will, a universe grown old. Not old in human terms, not even old in geological terms, but old beyond all comprehension. A universe where the last star flickered out trillions of years ago, where galaxies have long since dispersed into the cosmic dark, and where the very protons that make up atoms have decayed into lighter particles and energy. This is not a universe of fire and explosion, but one of gentle fading, of energy slowly spreading until everything reaches the same cold, uniform temperature. This is the heat death of the universe, and it represents one of the most elegantly inevitable conclusions that emerges from our understanding of how energy and entropy work on the grandest possible scale. The concept of heat death doesn't require any catastrophic events, no cosmic collisions or reality-breaking paradoxes. Instead, it follows naturally from one of the most fundamental laws of physics, the second law of thermodynamics. This law tells us that in any isolated system, entropy always increases over time. Entropy, in its simplest terms, is a measure of disorder or randomness, but more precisely, it quantifies how energy is distributed throughout a system. The universe, being the ultimate isolated system, must follow this inexorable trend toward increasing entropy. What this means is both beautiful and haunting. Over vast spans of time, all the energy in the universe will gradually spread out and even out, like heat flowing from a warm cup of tea into the cool air around it, until everything reaches the same temperature. When that happens, there will be no more temperature differences to drive engines, no gradients to power chemical reactions, no flows of energy to sustain the complex processes we call life. The universe will have reached what physicists call thermodynamic equilibrium, a state of perfect uniformity where no further work can be performed. This isn't just theoretical speculation. We can see the early stages of this process happening right now. Stars are already converting their nuclear fuel into heat and light, radiating that energy into space, where it slowly cools and disperses. Galaxies are drifting apart as space itself expands, making the universe larger and cooler with each passing moment. Even now, as you listen to these words, the cosmos is taking tiny steps along the path toward its ultimate equilibrium. The story of heat death begins in the 19th century with Lord Kelvin, who first applied the principles of thermodynamics to the universe as a whole. Kelvin realized that if the universe were like a giant steam engine, then just like any engine, it would eventually run out of usable energy. He also formulated what became known as Kelvin's paradox. If the universe were infinitely old, it would already have reached thermodynamic equilibrium. The fact that we still see stars shining, temperature differences persisting, and complex processes unfolding around us is evidence that the universe had a beginning and is still evolving toward its final state. This insight was revolutionary because it suggested that the universe itself was subject to the same physical laws that governed the mechanical systems of Kelvin's era. The same principles that explained why steam engines needed fuel and why hot objects cooled down also determined the ultimate fate of everything that exists. It was the first scientific framework for understanding cosmic evolution and the finite nature of universal processes. The heart of this story lies in understanding what entropy really means on a cosmic scale. Think of entropy not as chaos or mess, but as the number of ways energy can be arranged in a system. A hot star surrounded by cold space represents a very specific, organized arrangement of energy. There are relatively few ways to have all that nuclear fire concentrated in one place, while the surrounding space remains cold. But there are countless ways to have that same energy spread out evenly through space, with no particular region being hotter or colder than any other. The second law of thermodynamics is essentially a statement about probability. Systems naturally evolve from less probable arrangements to more probable ones, from organized states to disorganized ones, from concentrated energy to dispersed energy. It's not that the universe has a preference for disorder, it's simply that there are so many more ways to be disordered than to be ordered. Given enough time, any system will explore all possible arrangements, and the overwhelming majority of those arrangements look like equilibrium. When we apply this thinking to the entire universe, we get a picture of cosmic evolution that spans timescales almost beyond imagination. For now, we live in what cosmologists call the stelliferous era, when stars shine brightly and galaxies spiral majestically through space. But this is just one brief chapter in a much longer story. Stars will continue to form for perhaps another trillion years, but eventually, the supply of hydrogen gas needed for star formation will be exhausted. As existing stars burn through their fuel and die, the universe will slowly grow darker. The longest-lived stars, small red dwarfs that burn their fuel with extraordinary efficiency, will be the last lights in the cosmic night. These stellar embers can shine for tens of trillions of years, but even they will eventually exhaust their nuclear fuel. When the last red dwarf finally fades, the stelliferous era will end, and the universe will enter what cosmologists call the degenerate era. During the degenerate era, which may last from about a quadrillion years to a duodecillion years after the Big Bang, the universe will be populated by the remnants of stellar evolution. White dwarf stars, neutron stars, and black holes. These objects will slowly cool and fade, radiating away their remaining energy into the growing coldness of space. White dwarfs will gradually cool from white-hot to red to black, while neutron stars will slow their rotation and dim their magnetic fields. But even these stellar corpses are not permanent. According to some theories in particle physics, protons themselves may be unstable, slowly decaying into lighter particles over timescales of about 10 to the 34th power years. If proton decay occurs, then all ordinary matter, everything made of atoms, will gradually disintegrate. The white dwarfs and neutron stars will slowly evaporate, their constituent particles breaking apart and dispersing into space as electrons, neutrinos, and photons. When the last remnants of matter have decayed away, only black holes will remain, dominating what cosmologists call the black hole era. These gravitational monsters, some containing the mass of entire galaxies, will be the last large-scale structures in the universe. But even black holes are not eternal. Stephen Hawking showed that black holes emit radiation, slowly converting their mass into energy and gradually shrinking over time. The evaporation of a black hole is an almost unimaginably slow process. A black hole with the mass of our Sun would take about 10 to the 64th power years to evaporate completely. The largest supermassive black holes, containing billions of solar masses, might persist for 10 to the 100th power years or more. But eventually, even these cosmic titans will give up their last particles to the void. When the final black hole evaporates in a brief flash of radiation, the universe will enter its ultimate phase, the dark era. Space will be filled with a thin gas of elementary particles, electrons and photons scattered so widely that they rarely interact. The temperature will approach absolute zero, and the expansion of space will have stretched the universe to such enormous scales that the remaining particles are separated by distances larger than the observable universe today. This is heat death, not a violent explosion or catastrophic collapse, but a gentle fading into uniformity. Every region of space will have the same temperature, the same density, the same lack of activity. There will be no temperature differences to drive engines, no energy gradients to power reactions, no complex structures or processes. The universe will have achieved perfect equilibrium, and in that perfection, it will find a kind of eternal stillness. It's important to understand that this scenario depends on our current understanding of physics and cosmology. There are still many unknowns that could change the story. Dark energy, the mysterious force that appears to be accelerating the expansion of the universe, might behave differently in the future than it does today. The laws of physics themselves might change over such vast timescales, and there's always the possibility that new discoveries will reveal aspects of the universe we haven't yet imagined. Some cosmologists have proposed alternative endings for the universe. If dark energy continues to strengthen, it might eventually become so powerful that it overcomes all other forces, literally tearing apart the fabric of space and time in what's called the Big Rip. In this scenario, the universe would end, not in a gentle fade, but in a catastrophic unravelling, with space expanding so rapidly that it rips apart galaxies, stars, planets, and eventually even atoms themselves. Another possibility involves the nature of the vacuum itself. Some theories suggest that what we think of as empty space might not be in its most stable state. If the vacuum were to undergo a phase transition, it could release enormous amounts of energy, potentially destroying everything in the universe and replacing it with something entirely different. Such a vacuum decay event would propagate at the speed of light, giving no warning and no chance for escape. But for now, based on our best understanding of physics, heat death remains the most likely fate for our universe. It's a future that seems almost impossibly distant, separated from us by timescales that dwarf the entire history of everything we know. The universe is currently about 14 billion years old, which means it has existed for roughly 1/10 trillionth of the time it will take for the last stars to burn out, and an incomprehensibly smaller fraction of the time until heat death. In many ways, this distant future seems abstract, almost fictional, but there's something profoundly moving about contemplating these ultimate timescales. They remind us that we live in a universe that had a beginning and will have an end, that the energy that powers our thoughts and dreams is part of an ancient flow from order to disorder, from structure to uniformity. The warmth of your body, the light from your screen, the electrical activity in your brain, all of these are temporary eddies in the great current of entropy, brief moments of complexity in the universe's long journey towards simplicity. Yet there's also something deeply comforting about the heat death scenario. It suggests that the universe will end, not in violence, but in peace, not in catastrophe, but in rest. After eons of stellar birth and death, of galaxies colliding and black holes merging, of countless worlds arising and passing away, The cosmos will finally find perfect tranquility. Every atom that ever was will have played its part in the great story, and in the end, all will be equal, all will be still, all will be at rest. The concept of heat death also raises profound questions about meaning and purpose in a universe with a finite lifetime. If everything is destined to fade away, what significance do our actions have? What value is there in love, art, discovery, or kindness if all will eventually be forgotten in the cosmic dark? Perhaps the answer lies not in the destination, but in the journey. We are incredibly fortunate to exist during the universe's most vibrant and creative epoch, when stars are forming, planets are evolving, and consciousness has emerged to contemplate its own existence. We are part of the universe's attempt to understand itself, temporary arrangements of matter and energy that have somehow become capable of wonder, beauty, and love. The fact that our time is limited doesn't diminish its value. It enhances it. Every moment of awareness, every act of kindness, every discovery about the nature of reality is precious precisely because it is finite. We are the universe's way of experiencing itself, and in our brief existence, we carry the flame of consciousness through the cosmic night. So as you drift towards sleep tonight, perhaps you can find peace in the knowledge that you are part of something vast and ancient and temporary. The atoms in your body were forged in the hearts of dying stars, and the energy that animates your thoughts has been flowing through the cosmos since the beginning of time. You are both infinitesimally small in the grand scheme of things, and infinitely precious as a conscious being capable of contemplating the ultimate fate of everything. The heat death of the universe may be the end of the story, but it is not the end of meaning. In the brief span between now and then, we have the extraordinary privilege of existing, of thinking, of feeling, of creating beauty and seeking truth. We are the universe's moment of self-awareness, its brief experiment in consciousness and compassion. And perhaps in some way we don't yet understand, the love and beauty and knowledge we create during our cosmic moment will somehow persist, encoded in the quantum structure of reality itself, a permanent part of what the universe has been and done and dreamed. The heat death may claim our bodies and our worlds, but the fact that we existed, that we loved, that we wondered about our place in the cosmos, becomes an eternal part of the universe's story. So sleep well, fellow traveller through space and time. You are part of something magnificent, something that began in fire and will end in silence, but in between has created wonders beyond imagining. The universe is vast and old and will be here long after we're gone, but right now, in this moment, you are its eyes and ears and heart. Rest easy in the knowledge that you matter, that your existence adds something beautiful to the cosmic story, and that the energy that makes you who you are will continue its ancient dance through space and time until the very last star fades and entropy finally claims its perfect, peaceful victory. Heat death represents one of the most profound transitions the universe will ever experience. We've already explored how the cosmos evolved from the first stars to the complex galaxies we see today, but now we must confront what lies ahead, the universe's slow descent into a state of maximum entropy. As we drift deeper into this cosmic story, we find ourselves in an era where the universe has already passed through its most vibrant phase. The stellar nurseries that once blazed with newborn stars are beginning to quiet. The galaxies we've come to know and love are slowly exhausting their reserves of star-forming gas. What we're witnessing isn't a sudden catastrophe, but rather a gentle, inexorable, aging process that will unfold over timescales so vast they challenge human comprehension. The concept of heat death emerges from one of the most fundamental laws in physics, the second law of thermodynamics. This law tells us that entropy, or disorder, always increases in an isolated system, and the universe, being the ultimate isolated system, must follow this rule. As energy spreads out and becomes more evenly distributed, the temperature differences that drive all the processes we know will gradually disappear. Think of it this way: a hot cup of coffee will always cool down to match the temperature of the room around it. The heat doesn't vanish, it simply spreads out until everything reaches the same temperature. On a cosmic scale, the universe is like an enormous cup of coffee, slowly cooling and spreading its energy until no temperature differences remain. This process has already begun. The universe today is far cooler than it was in its youth. The cosmic microwave background radiation, that ancient afterglow of the Big Bang, has cooled from thousands of degrees to just a few degrees above absolute zero. Stars, those great fusion furnaces that have illuminated the cosmos for billions of years, are already becoming less common as the raw materials needed to build them grow scarce. But heat death isn't just about temperature. It's about the gradual cessation of all the processes that make the universe interesting. Without energy gradients, there can be no work, no motion, no chemistry, no life. Everything will eventually reach a state of perfect equilibrium, a cosmic stillness where nothing new can happen. The timeline for this transformation stretches far beyond anything we can easily imagine. We're not talking about millions or even billions of years, but trillions upon trillions of years. The sun will have exhausted its fuel and died long before heat death becomes a concern. Even the longest-lived stars, those small red dwarfs that burn their hydrogen so efficiently, will eventually flicker out. Yet there's something oddly peaceful about this ultimate fate. Heat death isn't a violent end like some cosmic catastrophes we might imagine. It's more like the universe slowly drifting off to sleep, settling into a state of a perfect eternal rest. The same physical laws that gave birth to stars and galaxies and consciousness itself will gently guide everything toward this final equilibrium. As we contemplate this distant future, we're reminded of our place in the cosmic story. We exist during what may be the universe's golden age, when stars still shine and galaxies still dance across the void. The energy that powers our thoughts, our dreams, our quiet moments like this one, is part of the same cosmic flow that will one day reach its peaceful conclusion. So as you settle into rest tonight, remember that you're participating in the universe's own grand rhythm. The warmth you feel, the gentle stirring of air around you, even the soft firing of neurons in your drowsy brain. All of this is part of the same energy flow that connects us to the deepest workings of the cosmos. And while the universe may one day reach its final quiet equilibrium, for now, in this moment, we are part of its beautiful, ongoing story. Now we enter perhaps the most dramatic chapter of our cosmic story. The universe has reached middle age. Galaxies have settled into their grand spirals and elliptical forms. Stars continue their ancient cycles of birth and death. But beneath this seemingly eternal dance, something profound is stirring. The very fabric of space itself is changing, and with it, the ultimate destiny of everything we know. This is the story of heat death, the universe's slow, inevitable journey toward a state of perfect equilibrium. It's not the violent end you might expect from science fiction. No explosions or cosmic catastrophes. Instead, it's a gentle fade, a gradual cooling, a whisper of entropy that grows quieter and quieter until finally there is only silence. Let's begin with a simple truth that governs everything around us. Energy always seeks balance. Like water flowing downhill or warm air mixing with cold, the universe has an irresistible tendency to even things out. This principle, enshrined in the second law of thermodynamics, tells us that entropy, the measure of disorder in a system, always increases over time. Think of it this way: if you drop a sugar cube into a cup of coffee, the sugar doesn't spontaneously reassemble itself. The milk you pour in doesn't separate back out. The heat from your coffee gradually spreads into the surrounding air until everything reaches the same temperature. These everyday examples reflect a cosmic truth. Order naturally gives way to disorder, and energy naturally spreads out until it can spread no more. The universe, vast as it is, follows the same rules. It began in a state of incredible order and energy concentration during the Big Bang. But from that first moment, entropy has been doing its patient work, spreading energy more and more evenly throughout space. Stars burn their fuel and radiate heat into the cosmic void. Galaxies drift apart as space itself expands, and slowly, inexorably, the universe moves toward a state where all energy is distributed as evenly as possible. This final state is what we call heat death, though the name is somewhat misleading. It's not about heat in the way we usually think of it. Rather, it's about the absence of temperature differences. In a heat death universe, there would be no hot stars and cold space, no warm planets and frigid moons. Everything would exist at the same uniform temperature. And without temperature differences, no work can be done, no energy can flow, and no complex processes can occur. The timeline for this cosmic ending stretches almost beyond comprehension. We're not talking about millions or even billions of years, but timescales that make the current age of the universe seem like a brief moment. The journey toward heat death unfolds in stages, each lasting longer than the last, each moving us closer to that final, quiet equilibrium. We currently live in what astronomers call the stelliferous era, the age of stars. This is a vibrant time in cosmic history, when nuclear furnaces light up the darkness and heavy elements are forged in stellar cores. But even this era has its limits. Stars can only shine as long as they have fuel to burn, and that fuel is not infinite. The smallest stars, red dwarfs barely massive enough to sustain fusion, are the universe's marathon runners. They burn their hydrogen so slowly and efficiently that they can shine for trillions of years. Our own sun, by comparison, is a sprinter that will exhaust its fuel in mere billions of years. But even the most miserly red dwarf will eventually consume its last atom of hydrogen, swell briefly, and then fade to a cold, dark ember. As the eons pass, star formation will slow and eventually cease altogether. The great stellar nurseries, the nebulae where new stars are born, will run out of raw material. The universe will grow darker as existing stars burn out and no new ones take their place. This transition marks the end of the stelliferous era and the beginning of the degenerate era. In this new age, the universe will be populated by the remnants of dead stars, white dwarfs, neutron stars, and black holes. These objects will drift through space like cosmic monuments to a more energetic past. White dwarfs, the dense cores of sun-like stars, will slowly radiate away their remaining heat over trillions of years, cooling from white-hot to red to infrared to black. Neutron stars, the incredibly dense remnants of massive stars, will gradually slow their rotation and fade from view. But even these stellar corpses are not permanent. If current theories are correct, protons themselves, the building blocks of ordinary matter, are not stable forever. Given enough time, perhaps 1034 years, protons will spontaneously decay into lighter particles. This means that white dwarfs, neutron stars, and even planets will slowly disintegrate, their atoms literally falling apart into a dilute gas of electrons, neutrinos, and photons. The timescales involved are staggering. To put 10 or 34 years in perspective, this is a 1 followed by 34 zeros. If the current age of the universe, about 14 billion years, were compressed into a single second, then 10 or 34 years would still be longer than a trillion years. It's a span of time so vast that it challenges our ability to comprehend it. Even after ordinary matter has decayed away, the universe will not be empty. Black holes, those gravitational monsters that swallow everything in their vicinity, will remain. In fact, they will dominate what's left of the cosmos, but even black holes are not eternal. According to Stephen Hawking's groundbreaking work, they slowly evaporate by emitting radiation. This Hawking radiation is incredibly faint for large black holes. A black hole with the mass of our Sun would take about 10^64 years to completely evaporate. The supermassive black holes that lurk at the centres of galaxies, with masses millions or billions of times that of the Sun, would persist for even longer, perhaps 100 years or more. But persist they will, slowly shrinking as they radiate away their mass energy. Near the end of their lives, as they become smaller and smaller, the rate of evaporation accelerates. The final moments of a black hole would be spectacular, a brief flare of energy in an otherwise cold and empty universe. And then, after the last black hole has evaporated, we enter the Dark Era. This is the final chapter of cosmic history, a time when the universe consists of nothing but a thin gas of elementary particles, electrons, neutrinos, and photons, all drifting through an ever-expanding void. The density of matter would be so low that these particles would rarely interact. The universe would be vast, cold, and essentially empty. In this far future, the temperature of space would be unimaginably close to absolute zero. There would be no stars to provide warmth, no planets to harbour life, no complex structures of any kind. The universe would have reached thermodynamic equilibrium, the state where entropy is maximised, and no further work can be performed. This is heat death. Not a violent ending, but a gentle fade into uniformity. It's the ultimate triumph of entropy, the final vindication of the second law of thermodynamics. All the energy that once powered stars and galaxies, that once drove the complex chemistry of life, would be spread so thinly and evenly that it could no longer accomplish anything interesting. Yet even in this seemingly barren future, the universe might not be completely static. Quantum mechanics suggests that even empty space is filled with quantum fluctuations, tiny bursts of energy that appear and disappear according to the uncertainty principle. Over the vast timescales of the Dark Era, these fluctuations might occasionally create something remarkable, a random assembly of particles that forms a brief, unlikely structure. Some physicists have speculated about Boltzmann brains, hypothetical conscious observers that could spontaneously form from quantum fluctuations. The probability of such an event is vanishingly small, but given infinite time, even the most unlikely events become inevitable, so perhaps, in the deepest future, the universe might occasionally flicker with brief moments of complexity and even consciousness, like sparks from a dying fire, but these would be rare and fleeting exceptions to an overwhelming rule of emptiness and cold. For all practical purposes, heat death represents the end of the universe as a place where interesting things can happen. It's a far cry from the hot, dense, energetic cosmos of the Big Bang, where every cubic centimetre of space was filled with potential. The journey from that initial burst of creation to the final whisper of heat, death spans an almost incomprehensible range of time and change. We live in what might be called the universe's brief spring, when stars shine brightly and planets dance around them, when complex chemistry gives rise to life and consciousness. This era, precious as it is just a tiny fraction of the cosmic story. Does this mean our existence is meaningless in the face of such vast timescales? Not necessarily. The fact that we exist at all, that the universe has organised itself into structures complex enough to contemplate their own fate, is itself remarkable. We are the universe becoming aware of itself, if only for a brief moment in cosmic time. Our star will eventually die. Our planet will be consumed or frozen, and our galaxy will slowly dissolve into the expanding void. But the patterns we've created, the information we've processed, the love we've shared, and the beauty we've appreciated are all part of the universe's temporary but magnificent experiment with complexity and consciousness. In a sense, we are living in the universe's golden age, when energy gradients still exist to power the intricate dance of life and thought. The future may hold only cold and darkness, but the present holds warmth and light, and the extraordinary fact that matter has organized itself into forms capable of wonder. The heat death of the universe is not a tragedy to be mourned, but a natural consequence of the physical laws that made our existence possible in the first place. The same thermodynamics that will eventually level all temperature differences also powers the stars that warm our planet and the metabolism that keeps us alive. We are both products of and witnesses to the universe's long journey toward equilibrium. So as we drift towards sleep tonight, let's appreciate the warmth of our beds, the gentle circulation of air in our rooms, and the quiet hum of energy flowing through the world around us. These simple comforts exist because the universe is still far from equilibrium, still capable of supporting the complex processes we call life. The cosmos may be destined for a cold and empty future, but for now, it sparkles with stars and swirls with galaxies, hosts planets, where oceans crash against shores, and where conscious beings contemplate the mystery of existence. In the vast sweep of cosmic time, this moment of awareness is fleeting, but it is also precious beyond measure, a brief candle flame in the darkness, beautiful precisely because it cannot last forever. Heat death may be the universe's ultimate destination, but the journey there has given rise to everything we know and love. And that, perhaps, is miracle enough. Now that we've wandered through the gentle mathematics of entropy and glimpsed the universe's ultimate destination, let's take a slow, contemplative journey through time itself. Not the kind of time you measure with clocks or calendars, but cosmic time, the vast, patient rhythm by which the universe ages and evolves. We're going to drift forward through billions upon billions of years, watching as the cosmos gradually transforms from the vibrant, star-filled arena we know today into something quieter, darker, and ultimately still. Think of it as watching the universe's biography unfold in slow motion, each chapter spanning more time than the human mind can truly grasp. We'll see stars exhaust their fuel, galaxies grow old and quiet, and the very fabric of matter itself begin to unravel. It's a story told not in moments or lifetimes, but in epochs so vast they make the entire history of Earth seem like a single heartbeat. The universe today, some 13.8 billion years after the Big Bang, is still relatively young and energetic. Stars are being born in stellar nurseries. Galaxies are colliding and merging. Black holes are growing, and the cosmic web continues to evolve. But this bustling activity won't last forever. Like a grand fireworks display, the universe's current spectacular phase is temporary, destined to fade into something altogether more subdued. To understand this cosmic timeline, astronomers have divided the universe's future into distinct eras, each characterized by the dominant processes and objects of that time. We're currently living in what's called the stelliferous era, the age of stars. It's a time when nuclear fusion in stellar cores provides the primary source of energy and light in the cosmos. But this era, for all its brilliance, represents just a tiny fraction of the universe's total lifespan. The stelliferous era began roughly 100 million years after the Big Bang, when the first stars ignited, and it will continue for approximately 100 trillion years into the future. That's an almost incomprehensibly long time, roughly 10,000 times longer than the universe has existed so far. During this era, stars will continue to form, live out their lives, and die, recycling their material back into space to fuel future generations of stars. But even the longest stellar lifespans have their limits. the most massive stars burn bright and die young, exhausting their nuclear fuel in just a few million years before exploding as supernova. Medium-sized stars like our Sun have longer, more sedate lives, burning steadily for about 10 billion years before swelling into red giants and eventually shedding their outer layers to become white dwarf stars. And the smallest stars, the red dwarfs, are the marathon runners of the stellar world, capable of burning their hydrogen fuel so efficiently that they can shine for trillions of years. It's these red dwarf stars that will dominate the final chapters of the stelliferous era. As larger stars exhaust their fuel and die, and as the supply of hydrogen gas needed for star formation gradually diminishes, the universe will become increasingly populated by these small, dim, long-lived stellar embers. They'll continue burning long after stars like our Sun have faded to cold, dark cinders, providing the last sources of starlight in an increasingly empty cosmos. But even the red dwarfs, patient as they are, cannot burn forever. Eventually, perhaps 50 to 100 trillion years from now, the last of these stellar lighthouses will flicker and die. The universe will enter a new phase, one astronomers have dubbed the degenerate era, named after the exotic matter that will dominate this period. The degenerate era represents a fundamental shift in the universe's character. No longer will nuclear fusion power the cosmos. Instead, the universe will be populated primarily by the remnants of dead stars, white dwarf stars, neutron stars, and black holes. These objects, made of what physicists call degenerate matter, are incredibly dense and exotic, held up not by thermal pressure like normal matter, but by quantum mechanical effects. White dwarf stars, the cooling remnants of stars like our Sun, will slowly radiate away their stored thermal energy over trillions of years, gradually fading from white to yellow to red to brown, and finally to black. They'll become cold, dark spheres of crystallized carbon and oxygen, drifting silently through space like cosmic diamonds that no longer catch the light. Neutron stars, the ultra-dense cores left behind by massive stellar explosions, will follow a similar path of gradual cooling. These objects, so dense that a teaspoon of their material would weigh as much as a mountain, will slowly spin down and fade, their powerful magnetic fields weakening as they radiate away their rotational energy. During this era, the universe will be a cold, dark place, illuminated only by the occasional flash of matter falling into a black hole, or the rare collision between stellar remnants. The temperature of space itself will have dropped to just a fraction of a degree above absolute zero, and the expansion of the universe will have stretched the cosmic microwave background radiation until it's virtually undetectable. But the degenerate era, vast as it is not the end of the story. Even these stellar remnants may not be permanent. According to some theories in particle physics, protons, the building blocks of atomic nuclei, may not be stable over extremely long time periods. If this is true, then even white dwarf stars and neutron stars will eventually decay, their constituent matter slowly disintegrating into lighter particles. The timescale for proton decay, if it occurs at all, is almost beyond imagination. Current experiments suggest that protons have a lifetime of at least 10 to the 34th power years. That's a number so large it makes the current age of the universe seem instantaneous by comparison. But if protons do indeed decay, then after approximately 10 to the 40th power years, all ordinary matter will have crumbled away, leaving behind only a thin soup of electrons, neutrinos, and photons. This would mark the beginning of the black hole era, a period when these gravitational monsters become the dominant objects in the universe. Black holes, which had been growing throughout the previous eras by consuming matter and merging with each other, would finally find themselves alone in an increasingly empty cosmos. But even black holes are not eternal. According to Stephen Hawking's groundbreaking work, black holes slowly evaporate by emitting radiation, a process now known as Hawking radiation. The smaller the black hole, the faster it evaporates. Stellar mass black holes would take an unimaginably long time to disappear completely, roughly 10 to the 67th power years. Supermassive black holes, the giants that lurk at the centers of galaxies, would persist even longer, taking up to 10 to the 100th power years to evaporate entirely. During their slow demise, these black holes would provide the last sources of energy in the universe. As they shrink, they would emit increasingly energetic radiation, briefly illuminating the cosmic darkness before finally disappearing in a final flash of gamma rays. With their departure, the universe would enter its final phase, the Dark Era. The Dark Era represents the ultimate fate of our cosmos, according to current understanding. It would be a time of unimaginable emptiness and cold, when the universe has expanded so much that individual particles are separated by distances larger than the observable universe today. The temperature would be essentially absolute zero, and no complex structures could form or persist. In this far future, the universe would consist mainly of a thin gas of elementary particles, electrons, neutrinos, and photons, all moving farther and farther apart as space continues to expand. Occasionally, quantum fluctuations might create brief random arrangements of particles, but these would be fleeting and without purpose or meaning. This timeline assumes that dark energy, the mysterious force currently accelerating the universe's expansion, continues to behave as it does today. But cosmology is full of uncertainties, and the ultimate fate of the universe depends on phenomena we don't yet fully understand. Dark energy might change its behavior, new physics might emerge at extremely long timescales, or quantum effects might become important in ways we haven't anticipated. Some theories suggest even more exotic possibilities. Virtual particles might occasionally fluctuate into existence for brief moments and over inconceivably long periods. These quantum fluctuations might even randomly assemble into complex structures, including, hypothetically, conscious observers called Boltzmann brains. These would be statistical miracles, conscious entities that spontaneously form from the random motion of particles existing just long enough to have a few thoughts before dispersing back into the void. But these speculations venture far beyond what we can confidently predict. What we can say with more certainty is that the universe's journey from its current vibrant state to the final heat death will be one of gradual cooling, increasing entropy, and growing isolation. It's a story of cosmic aging on a scale that dwarfs all human experience and imagination. Yet there's something oddly comforting about this vast timeline. It reminds us that the universe operates on scales far grander than our immediate concerns, following physical laws with patience and consistency that spans eons. The heat death of the universe, while inevitable, according to our current understanding, lies so far in the future that countless generations of stars will be born, live, and die before it arrives. Our sun will exhaust its fuel and become a white dwarf in about 5 billion years. The Milky Way and Andromeda galaxies will collide and merge in roughly 4 billion years. Complex life on Earth has existed for only a few 100 million years, and human civilization for mere thousands. Against the backdrop of cosmic time, we are living in the universe's energetic youth, surrounded by the light of active stars and the ongoing drama of cosmic evolution. The timeline of heat death teaches us that nothing in the universe is permanent, but it also reveals the extraordinary richness and complexity that can emerge from simple physical laws operating over vast periods of time. From the initial simplicity of the Big Bang, the universe has evolved into a cosmos filled with galaxies, stars, planets, and life itself. And while that complexity may eventually fade, the story it tells is one of remarkable creativity and persistence, As we drift through these cosmic timescales in our imagination, we're reminded of our place in this grand narrative. We are temporary arrangements of matter and energy, brief flickering flames in the cosmic dark. But we are also the universe becoming aware of itself, capable of contemplating its own future and finding meaning in the vast dance of particles and forces that surrounds us. The heat death may be the universe's ultimate destination, but the journey there is filled with wonder, beauty, and the ongoing possibility of new discoveries that might yet surprise us. In the meantime, we have stars to observe, questions to ask, and the remarkable privilege of existing during one of the most interesting and dynamic periods in cosmic history. So as you settle into sleep tonight, perhaps you can find some peace in knowing that while the universe may be heading toward a quiet end, that end lies unimaginably far in the future, beyond countless stellar generations and cosmic adventures yet to come. The heat death of the universe is real, but so is the magnificent, complex, ever-changing cosmos we inhabit right now, in this brief and precious moment of cosmic time. But here's where the timeline gets truly staggering, and where we need to zoom out, not just millions or billions of years, but to timescales that make the entire history of the universe so far look like the opening credits of an infinitely long movie. We're about to embark on a journey through deep time, where the stars themselves become temporary visitors, and where even the mightiest black holes eventually fade to whispers. Right now, we're living in what cosmologists call the stelliferous era, the age of stars. It's a glorious time, cosmically speaking. Stars are being born in stellar nurseries. Galaxies are spinning with brilliant spiral arms, and nuclear fusion is lighting up the cosmos with the warm glow of hydrogen burning into helium. From our perspective, this feels eternal, permanent, the natural state of things. But in the grand sweep of cosmic time, we're actually living during a brief and remarkable flowering. The stelliferous era began roughly 400 million years after the Big Bang, when the first stars ignited and began to shine, and it will continue for perhaps another trillion years, maybe a bit more. That sounds like forever, doesn't it? A trillion years from now, our sun will be long dead, the Earth will be a memory, and even the most optimistic projections for human civilization will have played out countless times over. But the universe itself will still be relatively young, still in the prime of its star-forming years. During this era, the cosmos has been remarkably productive. Stars form from collapsing gas clouds. They live their lives fusing lighter elements into heavier ones, and when they die, they scatter those elements back into space, enriching the interstellar medium for the next generation of stars. It's a cosmic recycling program that has been running for billions of years, building up the periodic table one supernova at a time. Carbon, oxygen, iron, gold, all the elements that make rocky planets and complex chemistry possible. They're all products of this stellar alchemy. But here's the thing about stellar recycling. It's not perfectly efficient. Each time gas gets processed through a star, some of it gets locked away in stellar remnants, white dwarfs, neutron stars, black holes, and some of it gets ejected so violently that it escapes from galaxies entirely, lost to the vast emptiness between galactic clusters. Slowly, gradually, the universe is running out of the raw materials needed to make new stars. The decline is already beginning, actually. Star formation in the Milky Way has been decreasing for billions of years. We're no longer in the wild, prolific star-forming epoch of the early universe, when galaxies were colliding regularly and triggering massive bursts of stellar birth. Today's universe is more sedate, more mature. The rate of star formation has dropped to perhaps 1% of what it was at its peak, roughly 10 billion years ago. As we move forward in time, this trend will continue. Stars will keep forming, but more and more slowly. The biggest, most massive stars will continue to live fast and die young, exploding as supernova after just a few million years. But gradually, the stellar population will be dominated by smaller, more modest stars, red dwarfs, those dim, long-lived stellar runts that can burn their hydrogen fuel with such miserly efficiency that they can keep shining for trillions of years. These red dwarfs will be the last lights in the cosmic darkness. Long after stars like our Sun have swelled into red giants and then collapsed into white dwarfs, long after the most massive stars have either exploded or collapsed into black holes, the red dwarfs will still be quietly burning their fuel, grain by grain. They're the universe's ultimate survivors, the cosmic equivalent of those deep-sea creatures that live around hydrothermal vents, making the most of whatever energy they can find. But even red dwarfs can't burn forever. Eventually, after tens of trillions of years, the last red dwarf will flicker and fade. The stelliferous era will end not with a bang, but with a barely perceptible dimming of the final star. And when that happens, the universe will enter a new phase, one that will last far, far longer than the age of stars ever did. This is the degenerate era, and it's when things start to get really quiet, with no more stars being born, and the last ones having finally died. The universe will be lit only by the slowly fading glow of stellar remnants. White dwarfs, those hot, dense cores left behind by sun-like stars, will cool gradually from white-hot to red to black, radiating away their thermal energy over timescales that dwarf the entire history of the cosmos so far. During this era, the universe will be populated by the compressed remains of stellar evolution, white dwarfs cooling like cosmic embers, neutron stars, those city-sized objects with the mass of suns slowly spinning down from their rapid rotation, brown dwarfs, the failed stars that never quite managed to ignite fusion, gradually cooling from their initial formation heat and scattered throughout, the black holes, invisible but massive, slowly accumulating whatever matter happens to wander too close. It will be a strange twilight universe. If you could somehow exist during this era, you might occasionally see the brief flare of matter falling into a black hole, or the collision of two white dwarfs, creating a temporary supernova. But mostly, it would be cold, dark, and incredibly lonely. The few sources of energy would be gravitational, things falling together, matter slowly settling into the lowest possible energy states. And yet, even this seemingly eternal twilight is just the beginning, because according to some theories, matter itself may not be stable over these vast timescales. Protons, those fundamental building blocks of atomic nuclei, might actually decay if you wait long enough. The experiments haven't detected it yet, but many theories of particle physics predict that protons have a finite lifetime, perhaps around 10 to the 34th years. That's a number so large it's almost meaningless. To put it in perspective, the universe is currently about 14 billion years old, which is roughly 10 to the 10th years. Proton decay, if it happens, wouldn't become significant until the universe is 10 trillion years old. But if protons do decay, then eventually all the white dwarfs, all the neutron stars, all the brown dwarfs, everything made of ordinary matter would slowly dissolve. The atoms that make up these stellar remnants would literally fall apart. The protons in their nuclei would decay into lighter particles, mostly electrons and neutrinos and photons. Over unimaginably vast timescales, all the matter that once made up stars and planets and galaxies would evaporate into a thin soup of the lightest possible particles. When that process is complete, after 10 to the 40th years or so, the universe will enter what cosmologists call the black hole era. By this point, black holes will be essentially the only large-scale structures left. Everything else, all the ordinary matter, will have decayed away. The universe will consist mostly of empty space, with black holes of various sizes scattered throughout like islands in an infinite, dark ocean. But even black holes aren't eternal. This is one of the most remarkable discoveries of 20th century physics, courtesy of Stephen Hawking. Black holes, despite their name, actually emit radiation. It's called Hawking radiation, and it's a quantum mechanical effect that occurs at the boundary of the black hole, the event horizon. The process is subtle and strange. Virtual particle pairs are constantly appearing and disappearing in empty space, a consequence of quantum uncertainty. Usually, these pairs annihilate each other almost instantly. But near a black hole's event horizon, sometimes one particle from a pair falls in while the other escapes. The escaping particle appears as radiation, while the black hole loses a tiny amount of mass energy to the particle that fell in. The amount of radiation is incredibly small for large black holes. A black hole with the mass of our Sun would take longer than 10 to the 64th years to evaporate completely. That's vastly longer than even the proton decay timescale. But smaller black holes radiate faster, and as a black hole shrinks, its temperature actually increases, causing it to radiate even more rapidly. This means that black hole evaporation is a runaway process. For most of its lifetime, a black hole barely radiates at all, but in its final moments, it becomes incredibly hot and bright, evaporating in a burst of high-energy radiation. The very last black holes to evaporate will be the supermassive ones that sit at the centers of galaxies. Some of these monsters contain billions of solar masses, and they'll take around 10 to the 100th years to finally fade away. When the last black hole evaporates, the universe will enter its final phase, the dark era. At this point, nearly all the mass energy that once made up stars and galaxies and planets will have been converted into radiation and the lightest particles. The universe will be a vast, coal-thin soup of photons and electrons and neutrinos, all gradually cooling and spreading apart as space continues to expand. The temperature will be unimaginably cold, far below anything we can achieve in laboratories today. The density will be so low that particles will be separated by distances larger than the entire observable universe is now. Occasionally, very rarely, particles might encounter each other, but mostly the universe will be empty, quiet, and incredibly, profoundly still. This is heat death, the final equilibrium state that thermodynamics has been driving toward all along. Not a fiery destruction, but a gradual fading into uniformity. The universe will have reached maximum entropy, the state where no more work can be done, no more complexity can arise, no more stories can unfold, and yet even this isn't necessarily the end of the story. Quantum mechanics suggests that, given enough time, truly enormous amounts of time, random fluctuations might occasionally create brief pockets of lower entropy. Perhaps, after 10 to the 10 to the 50th years, thermal fluctuations might spontaneously assemble something resembling a brain, complete with memories of a universe that died long ago. These hypothetical Boltzmann brains would exist for just a moment before dissolving back into the quantum foam, but they represent the universe's final desperate attempts to create something, anything, from nothing. It's a timeline that challenges our deepest intuitions about permanence and meaning. Everything we think of as eternal, stars, galaxies, even black holes, are just temporary features in a universe heading inexorably towards stillness. The age of complexity, the era when interesting things happen, represents just the tiniest fraction of cosmic history. But here's what I find remarkable about this story. We're living during the universe's most creative period, when stars are shining, when planets can form, when life can emerge and evolve and develop consciousness capable of understanding its own cosmic context. We exist during the brief window when the universe is complex enough to contemplate itself. In a sense, we are the universe's way of experiencing wonder at its own existence. Through our eyes, the cosmos gets to appreciate its own beauty, its own vast scales of space and time, its own elegant laws and inevitable fate. We may be temporary, but we're also the universe's most remarkable achievement, conscious beings capable of grasping both the glory and the tragedy of our cosmic situation. And perhaps that's enough. Perhaps meaning doesn't require permanence. Perhaps the fact that we're here now, in this moment, during this brief flowering of complexity and consciousness, is itself a kind of miracle worth celebrating, even as we contemplate the vast darkness that awaits. Now that we've glimpsed the early universe's violent birth and witnessed the first stirrings of galactic formation, let's drift deeper into one of the most profound questions that has ever haunted the cosmos. What happens when the music stops? What becomes of all those shining cities of stars, all those swirling spirals and glowing ellipticals when the universe itself grows old and tired? Welcome to the heat death of the universe, the Big Freeze, the final chapter in cosmic history where entropy wins, energy spreads thin, and the last light flickers out into eternal darkness. It's a story written in the language of thermodynamics, painted across billions of years and whispered in the dying breaths of the final stars. The heat death isn't a sudden catastrophe like the Big Rip, where space itself tears apart, nor is it a cosmic implosion like the Big Crunch. Instead, it's something far more subtle and inexorable. The universe's slow, graceful slide into perfect equilibrium. It's what happens when every last bit of usable energy has been spent, when all temperature differences have evened out, and when the cosmos reaches a state of maximum entropy from which no further work can be extracted. Picture, if you will, a vast cosmic engine that has been running for nearly 14 billion years. This engine has been powered by the fundamental forces of nature, fueled by the nuclear fires of stars, and driven by the relentless expansion of space itself. But like all engines, it's subject to the laws of thermodynamics, and those laws are unforgiving. They tell us that useful energy always flows from hot to cold, from concentrated to dispersed, from order to chaos, and eventually, inevitably, that flow must come to an end. The journey toward heat death begins not with a bang, but with a gradual dimming. We're already well into this process, though it's happening so slowly that entire civilizations could rise and fall without noticing the change. The universe today is a bustling place, filled with star-forming regions, active galactic nuclei, and all the complex chemistry that makes planets and life possible. But this abundance of activity is temporary, a brief flowering in the cosmic spring that cannot last forever. To understand how we reach this final state, we need to follow the universe through several distinct eras, each one cooler and darker than the last. We've already lived through the primordial era, when the universe was a hot, dense soup of fundamental particles. We're currently in the stelliferous era, the age of stars, which began roughly 1 billion years after the Big Bang and will continue for trillions of years to come. During the stelliferous era, hydrogen and helium gas collapse under gravity to form new stars, which burn their nuclear fuel and synthesize heavier elements in their cores. When these stars die, they scatter those elements into space, enriching the interstellar medium and enabling the formation of planets, complex molecules, and perhaps life itself. It's a time of incredible creativity and complexity, when the universe builds structures on every scale, from molecules to galaxy clusters. But even this golden age of star formation is finite. Stars require raw materials, specifically hydrogen gas, and the universe's supply isn't infinite. Every time a star is born, it locks up some of that precious hydrogen in nuclear reactions, converting it into helium and heavier elements. Some of this processed material gets recycled when massive stars explode as supernova, but each cycle is less efficient than the last. Gradually, inexorably, the universe's star-forming gas gets depleted. Current estimates suggest that star formation will peak and then begin to decline over the next few billion years. The universe will continue making new stars for roughly another trillion years, but the rate will steadily decrease. The largest, most massive stars burn through their fuel quickly and die young, leaving behind neutron stars and black holes. Medium-sized stars like our Sun will swell into red giants, shed their outer layers, and fade away as white dwarf stars. The smallest stars, the red dwarfs, will burn their hydrogen so slowly and efficiently that they could continue shining for tens of trillions of years. These red dwarf stars will be the last beacons of the stelliferous era. Long after our Sun has exhausted its fuel and the Milky Way has finished merging with Andromeda, these tiny stellar embers will continue their patient nuclear burning. But even they cannot burn forever. Eventually, the last red dwarf will exhaust its fuel supply, fade to a cool brown dwarf, and then to a cold black dwarf. When that happens, roughly 100 trillion years from now, the stelliferous era will end, and the universe will enter the degenerate era. The degenerate era is named after the exotic forms of matter that will dominate during this time: white dwarf stars, neutron stars, and black holes. These are the compressed remnants of stellar evolution, objects so dense that their matter exists in quantum mechanical states, unlike anything we encounter in everyday life. White dwarfs are roughly the size of Earth but contain the mass of the Sun, supported against gravitational collapse by the pressure of degenerate electrons. Neutron stars are even more extreme, packing more mass than the Sun into a sphere just 20 kilometers across, held up by the pressure of neutrons crushed together at nuclear density. During the degenerate era, these stellar remnants will slowly cool and fade. White dwarfs will radiate away their stored thermal energy over trillions of years, gradually dimming from white to yellow to red to infrared, eventually becoming cold black dwarfs, invisible against the cosmic background. Neutron stars will similarly cool, their surfaces dropping from millions of degrees to near absolute zero. But the degenerate era holds an even more profound transformation, one that strikes at the very heart of matter itself. According to certain theories in particle physics, protons, the building blocks of atomic nuclei, may not be stable forever. If these theories are correct, protons will spontaneously decay into lighter particles like electrons, neutrinos, and photons, with a half-life of roughly 10 to 34 years. This timescale is almost incomprehensibly long. If you took every proton in a human body and waited for one proton half-life, only half of them would have decayed. But given enough time, proton decay would fundamentally transform the universe. All atomic matter, everything made of protons and neutrons, would gradually disintegrate. The white dwarf and neutron star, remnants of ancient stars, would slowly evaporate, leaving behind only electrons, neutrinos, photons, and black holes. If proton decay occurs, it would mark the end of chemistry as we know it. No atoms could exist, no molecules could form, and no complex structures could persist. The universe would be populated only by a thin gas of elementary particles and the slowly evaporating black holes that once lurked at the centers of galaxies. This brings us to the black hole era, perhaps the strangest and most melancholy phase of cosmic evolution. During this era, which could last from about 10 or 40 to 100 years after the Big Bang, black holes will be the only organized structures remaining in the universe. Everything else, all the atoms and molecules and complex chemistry that once filled galaxies, will have either fallen into black holes or decayed into elementary particles. But even black holes are not eternal. In 1974, Stephen Hawking made one of the most profound discoveries in theoretical physics when he showed that black holes must emit radiation and slowly evaporate. This Hawking radiation arises from quantum mechanical effects near the black hole's event horizon, where virtual particle pairs spontaneously appear and one member of each pair falls into the black hole while the other escapes. The rate of Hawking radiation is inversely related to the black hole's mass. Tiny black holes evaporate quickly, while massive ones take an almost unimaginable amount of time to disappear. A black hole with the mass of our Sun would take about 10 to 67 years to evaporate completely. The supermassive black holes that lurk at the centres of galaxies, containing millions or billions of solar masses, would persist for 10 or 100 years or more. During most of its lifetime, a black hole's Hawking radiation is extremely faint and cold, mostly in the form of photons, with wavelengths larger than the black hole itself. But as the black hole shrinks, its surface temperature increases, and the radiation becomes more intense. In the final moments of evaporation, the black hole releases a burst of high-energy particles and gamma rays before disappearing entirely in a flash of light. One by one, all the black holes in the universe will undergo this process. The smallest will evaporate first, followed by larger ones, and finally by the supermassive giants that once powered quasars and shaped the evolution of galaxies. When the last black hole evaporates, perhaps 10 or 100 years from now, the black hole era will end, and the universe will enter its final phase. The dark era. The dark era represents the ultimate fate of our cosmos under the heat death scenario. By this time, the universe will be unimaginably vast, expanded to many times its current size, and filled with nothing but a dilute gas of elementary particles, electrons, positrons, neutrinos, and photons. The temperature will be very close to absolute zero, just a tiny fraction of a degree above the minimum possible temperature. In this final state, the universe will have reached thermodynamic equilibrium. There will be no temperature differences to drive heat engines, no concentration gradients to power chemical reactions, no sources of free energy to sustain complex processes. The second law of thermodynamics will have achieved its ultimate victory: maximum entropy, minimum useful energy, perfect and eternal stillness. The particles that remain will be spread so far apart that they will rarely interact. An electron might drift through space for billions of years without encountering another particle. The expansion of space will continue to stretch the distances between particles, making encounters even rarer as time goes on. The universe will become a vast, cold, empty expanse, punctuated only by the occasional quantum fluctuation. But even in this seemingly lifeless state, the universe may not be entirely devoid of interest. Quantum mechanics suggests that given enough time, truly enormous amounts of time, random fluctuations could spontaneously assemble complex structures. Particles might randomly come together to form atoms, molecules, or even more organized systems. There's even speculation about Boltzmann brains, hypothetical self-aware structures that could arise from quantum fluctuations over timescales of 10 mod 10, 50 years or longer. These fluctuations represent a kind of quantum resurrection, where the universe occasionally and randomly recreates fragments of its former complexity. But such events would be extraordinarily rare, separated by vast eons of emptiness and silence. They would be like brief candle flames flickering in an infinite darkness, beautiful but fleeting reminders of the universe's more creative past. The heat-death scenario assumes that our current understanding of physics is correct, and that no new phenomena will intervene to change the universe's fate. But science is always evolving, and there are aspects of cosmic evolution that remain deeply mysterious. Dark energy, which makes up about 68% of the universe's total energy density, is still poorly understood. If its properties change over time, it could alter the universe's expansion rate and ultimate destiny. There are also speculative ideas about how the universe might avoid or postpone heat death. Some theories suggest that quantum tunneling could allow the vacuum state to decay to a lower energy level, releasing enormous amounts of energy and potentially resetting cosmic evolution. Others propose that the universe might be cyclic, with periods of expansion followed by contraction and rebirth. These ideas remain highly speculative, but they remind us that our vision of the future is based on our current, incomplete understanding of the cosmos. Even if heat death is inevitable, the timescales involved are so vast that they dwarf all human experience and comprehension. The universe is currently about 13.8 billion years old, but the heat death scenario plays out over 100 years or more. That's a period roughly 1090 times longer than the current age of the universe. To put this in perspective, if the entire history of the universe, from the Big Bang to today, were compressed into a single second, the journey to heat death would take longer than the current age of the universe. From our perspective, nestled in the early warmth of the stelliferous era, heat death seems unimaginably remote. Stars are still being born in great numbers. Galaxies are still actively forming and merging, and the universe is still full of the energy and complexity that make phenomena like planets, chemistry, and life possible. We exist during what may be the most interesting and creative period in cosmic history, when the universe has cooled enough to form complex structures, but is still young and energetic enough to power them. This realization brings both humility and wonder. We are temporary patterns in the cosmic flow, brief arrangements of matter and energy that arose during a particular phase of universal evolution. Our existence and that of all life and consciousness represents a remarkable but finite flowering of complexity in a cosmos that is slowly but inexorably winding down. Yet there is also something profoundly beautiful about this cosmic story. The same physical laws that doom the universe to eventual heat, death, are the ones that made our existence possible in the first place. The nuclear fusion in stellar cores that will eventually run out of fuel is what created the carbon, oxygen, and other heavy elements in our bodies. The expansion of space that will ultimately dilute all energy also created the conditions for galaxies to form and stars to ignite. The heat death of the universe reminds us that we are part of something much larger than ourselves, participants in a cosmic drama that began with the Big Bang and will continue for eons beyond our ability to imagine. It encourages us to appreciate the remarkable complexity and beauty of the present moment, when the universe is still young enough to create and sustain wonders, like consciousness, love, art, and the scientific understanding that allows us to contemplate our own cosmic context. In the end, the heat death scenario is not just a prediction about the far future. It's a mirror that reflects back to us the preciousness and impermanence of our current cosmic epoch. We are living during the universe's most creative period, witnesses to its greatest achievements in complexity and beauty. That this flowering is temporary makes it no less magnificent. If anything, its transience makes it more precious, a brief and shining moment in the long, slow twilight of the cosmos. So as you drift off to sleep tonight, perhaps you can find comfort in knowing that you are part of this grand cosmic story, a conscious witness to the universe's most remarkable chapter. The stars will shine for trillions of years yet to come, providing light and warmth for countless generations of whatever life forms may evolve. And even when the last star finally fades and the universe settles into its final equilibrium, the story itself will remain, written in the quantum fluctuations of empty space, a permanent testament to the extraordinary complexity and beauty that once flourished in this cooling cosmos. The heat death may be the universe's ultimate destination, but the journey there is filled with wonders beyond imagination. We are privileged to be here for this part of the trip, conscious participants in the greatest story ever told. The concept of heat death is fascinating, but what happens to individual galaxies during this final era of the universe? While we've explored the grand cosmic timeline leading to maximum entropy, the fate of specific galactic structures during this transition deserves closer examination. During the approach to heat death, galaxies themselves undergo a slow but inexorable transformation. Even before the universe reaches its final state of maximum entropy, stellar formation within galaxies gradually ceases as the supply of hydrogen and helium gas becomes depleted. This process, known as galactic senescence, begins billions of years before the ultimate heat death. As star formation winds down, existing stars continue their life cycles, but no new ones replace them. The most massive stars burn out quickly in spectacular supernovae, while medium-sized stars like our Sun expand into red giants before collapsing into white dwarfs. The smallest stars, red dwarfs, continue burning for trillions of years, becoming the last beacons of light in an increasingly dark universe. The structure of galaxies also evolves during this period. Gravitational interactions between stars gradually redistribute their orbits through a process called stellar evaporation. Over extremely long timescales, some stars are ejected from their home galaxies entirely, while others spiral inward toward the central supermassive black hole. This process, taking approximately 10–19 years, slowly dissolves the organized structure of spiral arms and galactic disks. Meanwhile, galaxy mergers continue to occur, but with diminishing frequency as the universe's expansion carries galaxy groups farther apart. When mergers do happen, they create larger, more diffuse elliptical galaxies that consume their remaining gas reserves in brief starbursts before settling into quiescence. The supermassive black holes at galactic centers play an increasingly dominant role as normal matter becomes scarce. These gravitational monsters continue to grow by accreting the occasional star or gas cloud, but they also begin their own slow evaporation through Hawking radiation. For the largest black holes, this process takes an almost incomprehensible 10⁻100 years. During the final phases leading to heat death, galaxies become vast, cold collections of stellar remnants, white dwarfs, neutron stars, and black holes, orbiting in increasingly dispersed configurations. The space between these objects grows as the universe continues expanding, making gravitational interactions rarer and weaker. If proton decay occurs as some theories predict, even these stellar remnants eventually disintegrate, leaving behind only electrons, neutrinos, and photons in an ever-expanding, ever-cooling cosmos. The grand spiral and elliptical structures that once hosted billions of stars become nothing more than faint memories encoded in the universe's maximum entropy state. This galactic dissolution represents one of the most poignant aspects of heat death, not just the end of energy flow, but the complete erasure of the beautiful, complex structures that gravity spent billions of years constructing. Yet even in this ultimate fate, there's a certain elegance to how the universe's most fundamental laws guide both the creation and eventual dissolution of cosmic architecture. The transformation of galaxies during the approach to heat death reminds us that even the grandest structures in the universe are temporary, subject to the same thermodynamic principles that govern everything from steam engines to stellar evolution. In the end, the heat death scenario suggests that the universe's final state will be one of perfect uniformity. No galaxies, no stars, no structure at all, just the faint echo of ancient light scattered across an infinite, cold expanse after all the stars have died and all the black holes have evaporated away. After the last whisper of Hawking radiation has faded into the cosmic dark, we arrive at the strangest chapter in the universe's story. This is the Dark Era, and it's not quite the ending you might expect. Picture, if you will, a universe so vast and empty that particles are separated by distances greater than the observable universe today. The temperature has dropped to nearly absolute zero. There are no stars, no planets, no black holes, just elementary particles drifting through an endless, expanding void. This is what physicists call the heat death of the universe, though it's less of a death and more of a gentle fade to black. But even in this seemingly lifeless cosmos, something remarkable might still be happening. You see, quantum mechanics never truly sleeps, even in the depths of cosmic winter. Those same quantum fluctuations that helped create the first galaxies billions of years ago continue to ripple through the vacuum, occasionally doing something extraordinary. Every now and then, perhaps once in a Google years or maybe once in a Googleplex years, quantum fluctuations might spontaneously assemble matter from the void. Not just any matter, but potentially complex structures, atoms, molecules, and yes, in the most improbable twist of all, even conscious observers. These are called Boltzmann brains, named after the physicist Ludwig Boltzmann. They're hypothetical conscious entities that could randomly fluctuate into existence, complete with memories, thoughts, and the illusion of having lived a full life. In a universe with infinite time and space, even the most unlikely events become inevitable. It's a strange thought, isn't it, that in the deepest cold and darkness, consciousness might still flicker into being. A mind might open, experience a moment of awareness, perhaps even wonder about its place in the cosmos, before dissolving back into the quantum foam. These fleeting observers would outnumber all the conscious beings that ever lived during the universe's bright and lively epochs. But let's zoom out even further beyond individual particles and quantum fluctuations to consider the universe as a whole. Some theories suggest that even heat death might not be truly eternal. Perhaps the universe undergoes cycles, collapsing and rebirthing in an endless sequence of big bangs and big crunches. Or maybe vacuum decay will eventually rewrite the laws of physics themselves, creating entirely new realities from the ashes of our current cosmos. There's also the possibility that our universe exists alongside countless others in a vast multiverse. While our particular cosmic bubble slowly fades to black, others might be just beginning their own spectacular journeys through stellar formation, galaxy building, and perhaps even the emergence of life. The death of one universe could be balanced by the birth of another, somewhere in the infinite expanse of possibility. And then there are the truly exotic scenarios. Some physicists speculate about vacuum metastability, where our current universe exists in what's called a false vacuum. If this bubble of reality were to collapse, it wouldn't just end our universe, but potentially give birth to something entirely new, with different physical laws, different particles, different possibilities altogether. What's perhaps most beautiful about all these scenarios is how they remind us that endings might not be endings at all. The heat death of the universe represents maximum entropy, yes, but it also represents maximum possibility. When everything is spread evenly throughout infinite space, when energy can no longer flow from hot to cold because everything is the same temperature, the universe becomes a blank canvas upon which quantum mechanics can paint new stories. Even time itself becomes strange in this far future, without events to mark its passage, without clocks or observers or changing states. Time loses much of its meaning. Moments stretch into eternities, and eternities collapse into instants. The universe becomes timeless in the most literal sense, and yet for all its strangeness, this distant future connects directly to the present moment. Every breath you take, every thought you think, every star you see twinkling in the night sky is part of the same unfolding story that will eventually lead to those quiet, empty eons. The atoms in your body will outlast the sun, outlast the galaxy, and drift through space long after the last black hole has evaporated. In a sense, you're already part of the heat death of the universe. You're made of ancient stardust that has been recycling through the cosmos for billions of years. and you'll continue to be part of that cosmic recycling program long after your particular arrangement of atoms has moved on to other adventures. This is perhaps the most profound realization of all, that the end of the universe is not separate from its beginning, and neither is separate from this moment right now. The Big Bang, the formation of stars and galaxies, the emergence of life, and the eventual heat death are all part of one continuous story. You're not just observing this story from the outside. You're written into it, woven through it, inseparable from it. So as we drift toward the end of our cosmic journey through time, remember that endings in the universe are never quite what they seem. The heat death might sound final, but it's really just another transformation, another phase in an endless dance of matter and energy, space and time, possibility and reality. Somewhere in that far future, in the gentle darkness between quantum fluctuations, the universe sleeps. But even sleeping universes dream, and who knows what wonders might emerge from those dreams. We've journeyed through the vast expanse of cosmic time, from the universe's fiery birth to the final dance of galaxies merging in the darkness. We've watched stars live and die, seen black holes slowly evaporate through Hawking radiation, and witnessed the gradual triumph of entropy over order. We've explored the possibility of vacuum decay, the strange emergence of Boltzmann brains, and traced the inexorable march toward maximum entropy. And now, here at the end of our cosmic story, we arrive at perhaps the most profound question of all. What does it all mean? The heat death of the universe isn't just a scientific prediction. It's a mirror that reflects back something fundamental about existence itself. When we peer into that distant future, when we imagine a cosmos grown cold and still, we're forced to confront the deepest questions about purpose, meaning, and our place in the grand scheme of things. It's beautiful in its own way, this final chapter written in the language of thermodynamics. Let's take a moment to appreciate what we've discovered together. The universe, for all its apparent chaos and randomness, follows exquisitely precise laws. The second law of thermodynamics isn't just an abstract principle. It's the heartbeat of reality itself, the gentle drumbeat that carries everything forward from order toward equilibrium. Every sunrise, every heartbeat, every thought flickering through your mind right now is part of this vast, slow procession toward balance. But here's what strikes me as remarkable about this story. The heat-death scenario doesn't diminish the universe. If anything, it makes every moment more precious. Knowing that stars will eventually exhaust their fuel, that galaxies will drift apart, that even black holes will fade away, doesn't make those phenomena less magnificent. It makes them miraculous. Against the backdrop of inevitable entropy, the fact that complexity emerged at all, that life sparked into being, that consciousness arose to contemplate its own existence, these aren't just statistical fluctuations. They're celebrations of possibility. Think about the timeline we've traced together, from the Big Bang to the formation of the first atoms, from the birth of stars to the emergence of heavy elements, from planetary formation to the spark of life, and eventually to minds capable of understanding their own cosmic context, each step built upon the last, creating islands of increasing complexity in an ocean trending towards simplicity. We are, quite literally, the universe awakening to itself, entropy's own children learning to read the story of their cosmic inheritance. The physicists tell us that information might be the most fundamental quantity in the universe. Every interaction, every quantum event, every decision and discovery adds to the total information content of reality. In this view, consciousness isn't separate from the physical universe. It's how the universe processes and stores information about itself. Every memory you form, every insight you gain, every moment of understanding contributes to the universe's growing self-awareness. You're not just observing the cosmos, you're helping it think. This perspective transforms the heat death from an ending into something more like a completion. Yes, the universe will eventually reach maximum entropy, a state where no more work can be done, no more complexity can emerge through the usual processes. But by then, if conscious beings persist in some form, the universe will have spent billions upon billions of years examining itself, understanding its own laws, perhaps even discovering principles we can't yet imagine. The final state won't be empty. It will be full, pregnant with the accumulated wisdom of cosmic ages. And who knows what forms that wisdom might take? We've touched on the possibility of Boltzmann brains, random fluctuations that briefly assemble into conscious observers. But perhaps there are other possibilities. Maybe advanced civilizations will find ways to encode their knowledge into the quantum vacuum itself, creating information structures that persist long after stars have died. Maybe consciousness will discover how to exist in the sparse, cold universe of the far future, finding beauty and meaning in patterns we can't currently perceive. The remarkable thing about the heat-death scenario is how it emerges from the same physical laws that allowed complexity to arise in the first place. The second law of thermodynamics, which drives the universe toward equilibrium, also creates the energy gradients that power stars, planets, and life itself. Entropy isn't the enemy of order. It's the engine that makes temporary order possible. Without entropy, without the flow from hot to cold, from concentrated to dispersed, there would be no sunlight, no chemistry, no evolution, no thoughts. This brings us to something profound about time itself. We experience time as flowing from past to future, and the arrow of time emerges from the increase of entropy. Our memories work because entropy is increasing, creating an asymmetry between past and future that allows cause and effect to have meaning. In a universe at maximum entropy, where nothing changes, time itself might become meaningless. The heat death isn't just the end of events, it's the end of time as we understand it. But even that ending carries a strange beauty. Imagine the universe in its final state, vast and quiet, filled with the fading whispers of ancient light. Every photon a messenger from a time when stars still burned. Every particle a remnant of structures that once teemed with activity. It would be a universe of pure memory, holding within its quantum states the entire history of cosmic evolution. In that silence, in that stillness, the story we've told together would still be true, written into the fundamental structure of reality itself. And perhaps that's the most human response to the heat death of the universe, to find meaning not in spite of endings, but because of them. We tell stories precisely because they end. We cherish moments because they pass. We build and create and love, knowing that everything is temporary. The universe's journey toward heat death doesn't negate the beauty of a sunset or the warmth of human connection. It makes these experiences more poignant, more precious. The ancient Greek philosopher Heraclitus said that no one steps into the same river twice, because it's not the same river and you're not the same person. The universe too is a river, flowing inexorably from past to future, from order to chaos, from beginning to end. But we're not just stepping into this river. We are the river. We're made of the same atoms forged in stellar cores, governed by the same laws that guide galaxies and govern quantum fluctuations. The universe isn't something we observe from the outside, it's something we participate in from the inside. So when we contemplate the heat death of the universe, we're really contemplating our own place in the cosmic story. We're temporary patterns in the flow of energy and information, brief moments of self-awareness in the universe's long dream. But temporary doesn't mean meaningless. If anything, it means the opposite. Every moment of consciousness, every act of love or creativity or understanding is a small victory against the tendency toward equilibrium. Not a permanent victory, but a real one. The poet Rainer Maria Rilke wrote that perhaps all the dragons in our lives are princesses who are only waiting to see us act, just once, with beauty and courage. Perhaps the heat death of the universe is like that too. What seems like the ultimate dragon, the final defeat of everything we hold dear, might actually be something else entirely. Maybe it's the universe's way of ensuring that the story we've been part of, the story of increasing complexity and growing awareness, has genuine meaning precisely because it doesn't last forever. In the end, the heat death of the universe teaches us something profound about existence itself. It reminds us that we live in the middle of an extraordinary cosmic story, during the brief and brilliant epoch when stars shine and life flourishes and minds can contemplate their own origins. We exist during the universe's most creative period, when entropy hasn't yet claimed dominion over complexity, when islands of order can still emerge from the sea of increasing randomness. This is our moment. This is our cosmic season. And what a season it is. Against all odds, in defiance of entropy's patient pull, we're here. Conscious, curious, capable of wonder. We can trace the history of atoms and predict the future of stars. We can feel love and create art and ask questions about our own existence. We are the universe's way of knowing itself. And for this brief cosmic moment, that's enough. The heat death will come, as all things must end. But it hasn't come yet. Right now, in this moment, stars are being born in distant nebulae. Somewhere, perhaps, life is taking its first tentative steps on a young planet. Somewhere else, maybe, another species is looking up at their night sky and wondering about their place in the cosmos, just as we do. The universe is still becoming, still growing, still surprising itself with new forms of beauty and complexity. And we're part of that becoming. We're not just witnesses to the cosmic story. We're authors of it, writing new chapters. With every choice we make, every connection we forge, every moment of understanding we achieve. So as we close this journey through deep time, as we step back from the edge of cosmic eternity and return to our own small lives and immediate concerns, let's carry with us this perspective. We are children of the stars, inheritors of billions of years of cosmic evolution, participants in the universe's grand experiment with consciousness and complexity. The heat death reminds us that none of this was guaranteed, that all of it is precious, and that our moment in the cosmic story is both infinitesimally brief and infinitely meaningful. The universe gave us this time, this awareness, this capacity for wonder. What we do with it, how we choose to love and create and understand, that's our gift back to the cosmos. In the face of entropy, in the knowledge of endings, we choose meaning, we choose connection, we choose to marvel at the extraordinary fact that the universe became aware of itself through us, and for a little while found it good. So here we stand, tiny observers in an immense cosmos, contemplating the ultimate fate of everything we know. The heat death of the universe may seem like a bleak conclusion, but it reveals something profound about our place in the cosmic story. We exist during the universe's most creative and dynamic epoch, when stars shine brilliantly, planets form, and consciousness emerges to ponder its own existence. The trillions of years that stretch ahead before heat death arrives are almost incomprehensible. Our sun will burn for another 5 billion years, galaxies will continue their cosmic dance, and countless worlds may yet harbour life and intelligence. Even as entropy marches toward its ultimate victory, the universe still has eons of stories left to tell. Perhaps the most remarkable aspect of heat death is not its inevitability, but what it teaches us about the present moment. Every star that lights the darkness, every planet that harbours complexity, every thought that sparks in a conscious mind represents a temporary triumph over the universe's tendency toward disorder. We are not separate from this cosmic evolution. We are its most extraordinary expression. In contemplating the end of time, we discover that our brief existence is not diminished by its transience, but made more precious. We are the universe awakening to itself, if only for a cosmic instant.